Right. So let's further go ahead and try and state all these conditions in a more systematic manner uh, by grouping it into the necessary conditions, first sufficient conditions, as well as the first order and second order criteria to be satisfied. Yeah. So based on this, for the problem of minimization in general, it could be a problem of optimization, but here we're considering again minimization. We can state first order necessary conditions, which is um, in short mentioned as FONC. Second order necessary conditions, second order sufficient conditions. It's important to note that at first order we don't have a sufficient condition because the derivative of a function being zero is never a sufficient condition for that function to be a minima, because it has minimum points, maximum points, and neither maximum nor minimum points. All these points, it's a bigger umbrella. Okay, it's a bigger subset as we talked earlier. So let's state it more systematically here. Let's consider FONC first. FONC, a point is, let's call that point x star. X star is a minimizer when is minimizer of the function f of x. When is it a minimizer? Minimizer. We can't say when it is a minimizer, but what is the first order condition which has to be satisfied here? If the first order condition f dash of x, or we can write it as d by dx of f of x star should be equal to 0. Is it a sufficient condition? No. So this is actually the, okay, I'm going to change. This is first order necessary condition. Why it is first order? Because we're using the first order derivative to state this condition. Why is it necessary? Already told. It's not necessary that a condition, I mean, every point satisfying this condition need not be a minima. It can be a maxima, it can be a minima, it can be neither maxima, minima. It all depends on the function. Okay, so this is the first order necessary condition. Now let's go to the second order. First, let's state the second order sufficient conditions on in light to what we have discussed in the last class. So we have stated if f double dash of x star is greater than 0, then it is a minimizer. Okay, so this condition, we've told over here that it is a sufficient condition, because whenever we have a point uh, where the second derivative is greater than 0, we can say it is a minimizer for a function f of x. But the caveat here is does every minima point satisfy this condition? No. So there is a high possibility that even though this condition is satisfied, it does not give you all the minima points. So you might miss out on few minima which don't satisfy this condition. Or yeah, the better way to put it into perspective is that there are some minima which doesn't satisfy this condition. We have seen the case of x, the function f of x is equal to x raised to 4. Its minimum point is at x equal to 0, but it does not satisfy the second order test. So this is a second order sufficiency condition. Okay. Uh, yeah, so this is the second order sufficiency condition for a minimizer. And how do we formulate a necessary condition so that we can also include the minimum points which does not satisfy this condition? So one more thing which has to be noted here is uh, second order sufficiency condition. It holds only for a strict minimum, minimizer. What is a strict minimizer? If we go to our lecture on minimizers, both global or local, a strict minimizer is a point which satisfies this condition. F x star is strictly less than f of x at that particular point. So SOSC, it holds only for a strict minimizer. So normally this is how often referred to as SOSC for strict minimizer. Okay, fine. Now let's try to make it broader. Let's try to put in uh, more points. Yeah. How do we extend this idea so that we can also include the points which are excluded by the sufficient condition? So if you see earlier with our example of f of x is equal to, let's try to make a necessary condition. Necessary condition is always broader. Okay. How do we formulate this? So if we saw earlier f of x is equal to x raised to 4, we have seen that what was the issue with the second derivative? Second derivative of x at x is equal to 0 was actually 0. In fact, it was not greater than 0. This was the second order sufficiency condition. So if we relax this condition a bit, and if we say f of double dash of x, I mean f double dash of x at x star, x is equal to x star, or yeah, a better way of writing this is f of x. I'm writing it multiple times just to make sure that you guys have got the idea what is of this notation. F double dash of x star. If f double dash of x star, if you relax this inequality, sorry, yeah, inequality a bit, then this becomes actually a necessary condition. This is actually the second order necessary condition for a minimizer. But we have to note here, when we're using this condition, the minimizer actually um, becomes a weak minimizer. Okay. It could be a minimizer. It also may or may not be a minimizer. It can overlap with from the maximizer, weak maximizer, all these possibilities, but we're just making sure that we're not missing out on a point, which is actually a minimizer by making the condition so strict that we indeed end up missing that minimizer point. Okay, so these are the necessary and sufficient conditions when it comes to a minimizer in single variable. And further, we have the proofs of all these concepts, which I'm skipping at this point. And then the next class will try to extend this idea to higher dimensional functions, which are real valued functions, but which takes vectors as inputs. Okay. So yeah, so this is actually more of a review of what we have studied earlier, what we knew earlier, but we have uh, tried to systematically arrange it, the conditions, and what is actually a minima, what is a global minima, what is a local minima, what are the necessary and sufficient conditions, the first order necessary conditions, second order sufficiency conditions, and second order necessary conditions for a point uh, for point to be a minimizer of a function f of x in single variable. Now we extend our idea further to the domain of the function being Rn. okay, which we'll deal in the next lecture.